Hello everybody. This is the enzyme inhibitors video. After watching this video, you should be able to find Km and Vmax from a Lineweaver-Burk plot. Write the chemical equations for the three types of inhibition that we'll talk about. Describe the three types of inhibition. Identify these three types of inhibition from a Lineweaver-Burk plot and describe how Km and Vmax are affected for each. And then distinguish the different forms of catalytic inhibition and explain how and why they differ. So we've been talking about enzymes for a while now, and I keep wanting to come back to this slide. So remember, the second requirement for life is the ability to catalyze reactions efficiently and selectively. And biochemists like to quantify selectivity and efficiency. These are Kcat, Km, and Kcat over Km. And we can do that in a number of ways, and we've primarily talked about substrate concentration. In this video, we're going to talk about inhibitors, and then later we might touch just a little bit on how pH and temperature affect the selectivity and efficiency of an enzyme. And again, quantify means that we are going to put numbers to these things. So just a brief recall from the effect of substrate concentration on enzyme activity. We were using Michaelis-Menten kinetics to quantify or figure out the Km and the Vmax. If you're given enzyme concentration, you can get to Kcat. And then eventually you'll get yourself to Kcat over Km. And this was work done by Michaelis and Menten. I think I went over Maud Menten just a little bit in a previous video, but here's Lenore Michaelis. He was a biochemist, a physical chemist, a physician, and he was from Germany. And Maud was a biochemist and a physician, and she was from Canada. So it turns out if you linearize the Michaelis-Menten plot, you get a Lineweaver-Burk plot. And these Lineweaver-Burk plots are often used to find Vmax and Km. So this is what it looks like. So it's a linear plot where the x-axis is 1 over V0. The y-axis is 1 over V0. And the x-axis is 1 over substrate. So it takes the Michaelis-Menten plot, the hyperbolic plot, and it linearizes it. So all of the points end up in roughly a straight line here in this region of the plot, the positive x and the positive y. And the Lineweaver-Burk not only linearizes it, but requires you to extrapolate or pull the line through the y and the x-axis. So what you get are intercepts, and Km is -1 over the x-intercept, and Vmax is 1 over the y-intercept. So it's really important that whenever you get the data for a linearized Michaelis-Menten, that you extrapolate, and that means just to carry that line all the way through the x and the y-axis for the Lineweaver-Burk so that you can get a y-intercept and an x-intercept. Also make sure that you don't forget that this has to be a -1 over the x, because Km will always cross in the negative x quadrant, so you got to get yourself a positive number. Okay. So I've got a couple examples here, and by a couple I mean one. And so this is a Lineweaver-Burk plot, and the line has been extrapolated through the x and the y-axis. So the Km for this, -1 over -2, which is of course just a half. 0.5, and then your units are over here, and that would be micromolar. So note that this is 1 over micromolar, but you will have put the 1 over micromolar here. So when you do the math, it will invert itself and the micromolar will come up to the top. And then here is Vmax, 1 over 2 as well. So again, that equals a half. And the units here are obviously inverted. So if you put second per millimolar on the bottom, when you do the math, that will also invert itself to be millimolar per second, which hopefully you recognize as the units for Vmax, and hopefully you recognize these as the units for Km. If you were given enzyme concentration, you'd be able to get to Kcat, because Kcat, remember, is Vmax over enzyme concentration. So the Lineweaver-Burk plot is really just a very simple way of looking at the Michaelis-Menten data. And it's not used in papers too often to report just substrate, the effective substrate concentration, because what happens in the Lineweaver-Burk is that the points that are used to make the line are not weighted equally. And what that means is that these points out here have a bigger effect on the slope of the line than these points down here. So if this dot were to move up even just a little bit, it would change almost the whole slope of this line, and then your extrapolation would be off. So we don't tend to use Lineweaver-Burk when we're just reporting how substrate affects enzyme activity. We do use it. It's a wonderful way to visualize the effect of an inhibitor on enzyme activity. So that's why we're introducing Lineweaver-Burk, is because it's a really great way, and it is a very popular way to represent inhibitor data. And here's my gratuitous shout out to Lineweaver and Burk. I promise this will be probably the last duo that I will show you. Both of them were American. Lineweaver was a physical chemist and Burk was a biochemist. And so Lineweaver-Burk I always had the E on Burk. There's not an E on Burk. Lineweaver-Burk plots can tell you something about the mechanism of inhibition. Okay, and what this then can be used for is this can be used to help design a more effective inhibitor. Cool. Okay, so we're going to talk first about reversible inhibition, and then I'm going to give, and the dogs, and then I'm going to give a quick shout out to irreversible inhibition. So do I wait to see if they're going to bark again or not? Okay. So reversible inhibition, this occurs when an inhibitor causes a temporary, keyword here is temporary, loss of activity. I'll put an E out here, temporary loss of enzyme activity. However, this activity is regained if the inhibitor, I should say if or when, the inhibitor is removed. Okay, so we've talked about reversible binding before, especially of a ligand to a protein or a substrate to an enzyme. And these the reversibility is really driven by the non-covalent interactions. Between enzyme and substrate, protein and ligand, and in this case, enzyme and inhibitor. So those weak non-covalent interactions facilitate the reversibility of these interactions so that they don't last for too long. They don't stay for forever. So we're going to talk about 3 different kinds. The first one we're going to talk about is competitive. Okay, a fluff wants to come in. He can't come in. And then we're going to talk about uncompetitive. And then we'll also talk about mixed. And these 2 right here are also allosteric. So when they bind, they will change the shape of the enzyme. Okay, here we go. Competitive inhibition. So we're going to do a whole bunch of different kinds of diagrams, and then there's going to be some words, and I hope that it all makes sense. So let's do Pac-Man. So competitive inhibition is exactly the way that it sounds, is that the substrate and the inhibitor compete for the active site. So in my Pac-Man diagram, this part right here is the active site. And I can either have substrate bind, I guess I'll make substrate yellow, okay, or I can have an inhibitor bind. And the key thing with competitive inhibition is that the inhibitor and the substrate must have a similar shape. You know where I wanted to put that is not there. Sorry, buddy. We'll come back for you. So like I said, the inhibitor and the substrate in competitive inhibition have similar shapes. So if S binds first, or S is able to bind before the inhibitor, then you form the ES. Okay? And then this carries on to E plus P. If, however, the inhibitor binds, then you get EI. Okay? And no product is formed from that. So what this, another way to represent this is we can have E plus S, and if S binds, then we form the ES, and everything proceeds as normal to E plus P. However, if I binds first, then we could get an EI interaction. This is, I'm sorry, that's hard to see. This right here is EI. We get EI, which of course will not continue on to product. Okay, so first of all, a couple hallmarks of this is that S and I, so S is substrate and I is inhibitor, are structurally similar. Okay? If you increase the concentration of S, you can overcome the effect from I. So if you increase substrate concentration so high, it's statistically more likely that S will bind, and S can then, you can overpower I in this context. So what does this look like in terms of Michaelis-Menten? So Michaelis-Menten here, V naught, that should be a little O, versus substrate concentration. And then, of course, we're going to take it to the Lineweaver-Burk because it's easier to see there. So this is 1 over V naught, 1 over S, substrate concentration. The black line here will be without inhibitor. And then I'll do, what was I doing? I guess I'll do green with inhibitor. So, because at high S concentrations, we can outcompete the inhibitor for the enzyme, what this ends up looking like is a less steep slope, but it still comes up to Vmax. So this line is with inhibitor. So here, Km has increased and Vmax is the same. What this looks like on a Lineweaver-Burk plot is that if Vmax is the same, I'm going to have to cross at the same point in the y-axis, and if Km increases, then I'm moving more towards the positive x. So the line would be here, and that is meant to cross through. Let's just make it look nice. There we go. And again, this right here is with inhibitor, and the black line is without. W/O is without inhibitor. So what you should see is that for a competitive inhibitor, at high substrate concentrations, you can outcompete the inhibitor for the enzyme. The substrate will outcompete the inhibitor, and you can get all the way back to your Vmax by filling up all the enzyme sites with substrate. And the Vmax then stays the same. Well, that's what I erased. Stays the same, and Km increases. And again, this is more easily shown or more easy to see in a Lineweaver-Burk. Let's see, do I have anything else I want to say about this? Nope. Okay. Uncompetitive. So uncompetitive is really interesting because here the order of binding matters a lot. Okay, so uncompetitive inhibitors are also allosteric. So please don't forget that part. They're also allosteric. And again, I'm going to do my Pac-Man. There we go. I'm going to do my Pac-Man enzyme. So I'll have my active site, again, is going to be this V. And then my allosteric site is going to be this empty sort of boxy shape. So the allosteric site here is simply not the active site. It is somewhere far or near, actually it could be either, far or near from the active site. But whatever binds at the allosteric site will not result in any sort of product formation. Okay, so in uncompetitive, the order of binding matters. So the first thing that happens is substrate binds first. My substrate yellow. I'll do a diamond this time. So the very first thing that happens is we form an ES. This is ES. And then if inhibitor is not present, this will proceed to E plus P or complete the catalytic transformation. However, if inhibitor is present, then inhibitor binds second. This will be my inhibitor. And substrate inhibitor, what happens is there is a change in conformation, this is the allosteric part, that causes E to bind really tightly to S. And I'm just going to write clamp onto, clamp down on substrate. And the effect of this is that substrate will either be changed, moved in the active site, so either catalysis does not occur, or it just doesn't leave as frequently, so we've like decreased the reversibility of this. So Km for the substrate is actually going down because binding is better or stronger. Okay? We cannot overcome, the inhibition cannot be overcome at high concentrations of substrate because the substrate doesn't bind where the inhibitor binds and vice versa. And also these molecules, inhibitor and substrate, are not structurally similar. Okay, so what would this look like in a chemical equation? So we have E plus S. You must form ES first. So again, the order of binding matters. So substrate will always bind first for uncompetitive. If there's no inhibitor around, or if the reaction is fast enough, we'll proceed to E plus P. However, if there is inhibitor around, then the inhibitor will bind and we get this ESI. So inhibitor bound to substrate, both bound to the enzyme. What this looks like for Michaelis-Menten, again, black here will be without the inhibitor, V naught 1 over substrate. Okay, so without the inhibitor. With the inhibitor, so Km is increasing, so we're actually going to have a sharper slope, but we never achieve Vmax again. So Km decreases, and Vmax also decreases. So Kcat's going to go down, but Vmax is going to go up. What this looks like on the Lineweaver-Burk is you get parallel lines. It's about as parallel as I can make them. We could just, these are all increasing inhibitor concentration here. So just continuing to increase inhibitor concentration will make these more and more parallel lines as you go further and further out. So just visually, you can see that when the lines do not intersect on Lineweaver-Burk, you know that you have uncompetitive. When you cross at the y-axis, it's a competitive inhibition. And then the very last one that we're going to talk about is mixed. So mixed inhibition is, I don't know, it's like the most complicated. There's just lots of moving parts. So again, Pac-Man enzyme. Mixed inhibition is also a flavor of allosteric inhibition. So there is an allosteric site that can bind the inhibitor. And here, the order doesn't matter. So either substrate binds first or inhibitor binds first. Okay, so either or can happen. So if substrate binds first, okay, we get substrate in here. And again, without the inhibitor, this could proceed on to E plus P, where catalysis does occur. and the substrate is converted to product. In the case that enzyme binds inhibitor first, okay, there's going to be an allosteric change, but it won't be so great that substrate can't bind. So it turns out that substrate in this case will bind second. If I go down this route, oh, this is getting uglier and uglier as I go, to form the ESI enzyme substrate inhibitor complex. If we start up here where enzyme binds substrate first, then the second part that will happen, if there's inhibitor around, inhibitor binds second, and basically all roads lead to enzyme substrate inhibitor complex. And so again, in mixed inhibition, the order doesn't matter. And the effect is sort of a population average. Where Km is increasing and Vmax is decreasing. So I'll write the chemical equation for this. It doesn't include the cartoon diagrams. And then we'll draw the Michaelis-Menten and the Lineweaver-Burk. Okay. So again, we have E and S, and we have I all mixed together. If I binds first, then we have EI, and then S binds second to get to the ESI, or substrate binds first to get to ES, and then inhibitor binds second, so plus I. And it is possible that some of the substrate in the ES could be converted into product, and that product will leave the enzyme, so you get E plus P. So again, like I said, this is a population average because either route is possible. So the Michaelis-Menten, again, black is without inhibitor. S. Okay. So what this ends up looking like is, so Km is going to go down and Vmax is going to go down. So this is with inhibitor. And on the Lineweaver-Burk, this is easy to see because they will cross somewhere in the negative X, positive Y quadrant. So you'll get these lines. Actually, I should have moved it out further because it's hard to see if I don't do it like here. 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 Maybe I'll do like a really crazy one here. So they all cross, they all intersect in this quadrant over here. And again, this is increasing inhibitor concentration. And the effect is Km is going up and Vmax is going down. Again, the inhibitor and the substrate are not structurally similar. And you can also not you cannot overcome this type of inhibition with a high concentration of S. Can't be done because they don't bind at the same site. And let's see, is there anything else I want to say about that? I don't think so, but I'm going to do one quick slide or one quick extra, I don't know what these things are called when I do this. button. But one quick recap so that you can see them all at the same time. Again, the black line represents without the inhibitor, V naught, 1 over S, 1 over V naught, 1 over S, 1 over V naught. Wow! Go back. 1 over S. For competitive inhibition, they will cross here at the y-intercept. For uncompetitive, the lines never cross. And for mixed, the lines will cross somewhere. I made that really close to the x-axis, but the lines will cross somewhere that is in the negative x, positive y quadrant. So again, this is competitive. This is uncompetitive, and this is mixed. So again, what is really nice about the Lineweaver-Burk is that as long as you can see how the lines are related to each other, you can easily identify competitive, uncompetitive, and mixed. And then you can say something about whether I is similar to S. Okay, whether I is allosteric, an allosteric effector, whether it's homotopic or tropic or heterotropic. Remember those words? I do. Anyways, so that's the beauty of the Lineweaver-Burk, because it's really easy to see the different types of inhibition, and then you can infer some things about what the inhibitor looks like and how it works. And we have one last type to talk about, and that's irreversible. And I'm just going to do a really quick shout out because it's like exactly what it sounds like. Many irreversible inhibitors covalently bind to their enzymes. When it is covalently bound, these are also called suicide inhibitors. Okay, because it basically annihilates the activity of the enzyme. That covalent bond is so strong that it is not likely to come off. So this is an example. Here's the enzyme. It has a little serine coming out of its active site. This is not to scale because diisopropyl fluorophosphate is not bigger than the enzyme. Please, I'm hoping that you can see that. Anyways, this serine right here can be a nucleophile to attack this phosphate. Electrons up, electrons down, and then it'll kick off this fluorine, which hopefully you remember is a pretty darn good leaving group. And then what's happened is you've created a covalent bond to this giant, well, I think it's giant, relatively large functional group that's not going to be able to be broken. There's no way to undo that covalent bond. So that enzyme active site is essentially no longer active. Nothing else is going to fit in there because this will be a physical block for any substrate. Will just bounce right back off because there's no space for it to fit in the active site. And that's it. I think that's all that I have. Have a good time with your homework, and I'll see you in class. Bye.